The National Electrical Code has always prohibited the direct connection of grounding conductors to neutral conductors. This requirement was first explicitly stated in the 1971 NEC, but has been implied in earlier editions. The 1996 NEC clarified this requirement and emphasized the need to maintain the integrity of the grounding system. Understanding the risks associated with tying ground to neutral is crucial for electrical safety. Firstly, there is the risk of overcurrent. If the neutral conductor becomes disconnected, the grounding conductor could carry hazardous currents, potentially causing electrical fires or shocks. Secondly, electrocution is a risk. If equipment with a fault develops, the flow of current through the grounding conductor could create a path to ground that may not have been intended, increasing the risk of electrocution. Thirdly, tying ground to neutral can interfere with the proper operation of ground fault circuit interrupters, or GFCIs. It is important to understand that some inspectors and electricians may have outdated knowledge or interpretations. It is therefore important to refer to the current NEC for accurate information. The NEC does not allow the installation of ungrounded GFCIs with 3 prongs. GFCIs require a proper grounding system to function correctly. Ungrounded GFCIs can provide limited protection against ground faults, but they cannot fully protect against all electrical hazards. Tying ground to neutral is a violation of NEC requirements and poses significant safety risks. Ungrounded GFCIs are not allowed by the NEC and do not provide adequate protection. It is essential to consult with qualified electricians and refer to the latest NEC for accurate information and safe electrical practices. Grounding and bonding are critical safety measures in electrical systems, and the NEC provides comprehensive guidelines to ensure these systems function effectively. Grounding refers to connecting electrical equipment and systems to the earth, providing a low impedance path for fault currents to return to the source. Bonding, on the other hand, involves connecting metallic parts of an electrical system to create an electrically conductive path, ensuring that all bonded components are at the same electrical potential. The purpose of grounding is to limit voltage to ground and to provide a path for fault current to facilitate the operation of overcurrent protective devices like circuit breakers and fuses. This helps prevent electrical shock hazards and reduces the risk of fire. Grounding also helps stabilize voltage during normal operation and reduces electrical noise. The NEC specifies different types of grounding systems, including grounded and ungrounded systems. In a grounded system, one conductor, usually the neutral, is intentionally connected to ground at the service entrance. This connection establishes a reference point for voltage and helps to limit the voltage to ground. In contrast, an ungrounded system does not have a direct connection to ground, but it may have a high impedance ground to limit fault current. Bonding ensures that all metal parts of an electrical system are electrically connected, creating a low impedance path for fault current. This path allows fault current to flow back to the source, tripping the overcurrent protective device and de-energizing the circuit. Bonding is essential for preventing shock hazards because it minimizes the voltage difference between metal parts. The NEC requires bonding of various metal components, including metal conduits, equipment enclosures, and metal water pipes. Proper grounding and bonding require the use of appropriate conductors and connectors. Grounding conductors must be sized according to the NEC tables based on the size of the overcurrent protective device. Bonding conductors must also be sized appropriately to handle the expected fault current. Connectors used for grounding and bonding must be listed for the purpose and installed according to the manufacturer's instructions. Ground fault circuit interrupters, or GFCIs, are devices designed to protect people from electrical shock. They work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 mA or more between the currents, the GFCI trips, quickly de-energizing the circuit. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC specifies the locations where GFCIs are required. These include bathrooms, kitchens, garages, outdoor receptacles, crawl spaces, unfinished basements, and near swimming pools. GFCIs can be installed as receptacles or circuit breakers. GFCI receptacles are installed in place of standard receptacles, while GFCI circuit breakers protect the entire circuit. When a GFCI detects a ground fault, it trips very quickly, typically within a fraction of a second. This rapid response time helps to prevent serious electrical shock. GFCIs are tested periodically to ensure they are functioning correctly. Test buttons on GFCI receptacles and circuit breakers simulate a ground fault, causing the device to trip. The NEC requires that GFCIs be tested monthly to verify their operation. Surge protection is important for protecting electronic equipment from voltage spikes and surges. Surges can be caused by lightning strikes, power outages, and other electrical disturbances. Surge protective devices, or SPDs, are designed to divert excess voltage away from sensitive equipment, preventing damage. SPD are installed at the service entrance, at branch panels, and at individual equipment locations. The NEC requires surge protection in certain applications, such as dwelling units and critical facilities. SPD are rated by the surge current capacity, which indicates the amount of current they can safely divert. SPD also have a voltage protection rating, which indicates the maximum voltage that will be allowed to pass through the device. SPD can be installed as hardwired devices or as plug-in strips. Hardwired SPD provide better protection because they are directly connected to the electrical system. Plug-in SPD are convenient for protecting individual pieces of equipment. Electrical panels, also known as load centers or distribution panels, are the heart of an electrical system. They distribute electricity from the service entrance to the various circuits in a building. Electrical panels contain circuit breakers or fuses that protect each circuit from overcurrent. The NEC specifies the requirements for electrical panels, including their location, installation, and wiring. Electrical panels must be accessible and located in a dry, well-ventilated area. They must be securely mounted and properly grounded. Circuit breakers and fuses are overcurrent protective devices that interrupt the flow of electricity when a fault occurs. Circuit breakers can be reset after tripping, while fuses must be replaced. The NEC specifies the types and sizes of circuit breakers and fuses that can be used in different applications. Circuit breakers are rated by their amperage and voltage. The amperage rating indicates the amount of current the breaker can carry before tripping, while the voltage rating indicates the maximum voltage the breaker can safely interrupt. The NEC provides tables for determining the correct size of circuit breakers and fuses for different circuits. These tables take into account the ampacity of the conductors, the type of load, and other factors. Wiring methods refer to the ways in which electrical conductors are installed and protected. The NEC specifies the types of wiring methods that can be used in different applications. Common wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, non-metallic conduit, and cable wiring. Each wiring method has its own advantages and disadvantages in terms of cost, ease of installation, and protection. Rigid metal conduit, or RMC, is a heavy-duty wiring method that provides excellent protection for conductors. It is typically used in harsh environments where there is a risk of physical damage. Electrical metallic tubing, or EMT, is a lightweight wiring method that is easy to install. It is commonly used in commercial and residential applications. Flexible metal conduit, or FMC, is a flexible wiring method that is used to connect equipment that may move or vibrate. Non-metallic conduit, such as PVC conduit, is a corrosion-resistant wiring method that is used in wet or corrosive environments. Cable wiring, such as NM cable, is a flexible wiring method that is commonly used in residential applications. Conductor ampacity refers to the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables that list the ampacity of different types of conductors based on their size, insulation type, and installation conditions. Conductor ampacity is affected by several factors, including ambient temperature, the number of conductors in a raceway, and the type of insulation. When conductors are installed in high-temperature environments or in groups, their ampacity must be derated to prevent overheating. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors must be sized appropriately for the length of the circuit and the amount of current they will carry. Electrical safety is paramount in all electrical work. It is essential to follow safe work practices and use appropriate personal protective equipment, or PP, to prevent electrical shock and other hazards. Before working on any electrical equipment, it is important to de-energize the circuit and verify that it is de-energized using a voltage tester. Lockout/tagout procedures should be followed to prevent accidental re-energization of the circuit. PPE for electrical work includes insulated gloves, safety glasses, and arc-rated clothing. Insulated gloves protect against electrical shock, safety glasses protect against arc flash, and arc-rated clothing protects against burns. Only qualified electricians should perform electrical work. Qualified electricians have the training and experience to safely install, maintain, and repair electrical systems. The NEC is a comprehensive set of standards for electrical installations. It is updated every 3 years to reflect changes in technology and best practices. It is important to consult the latest edition of the NEC for accurate information on electrical safety and installation requirements. State and local jurisdictions may have additional electrical codes and regulations that must be followed. These codes may be more stringent than the NEC in some areas. Electrical permits are required for many types of electrical work. Permits ensure that electrical installations are inspected and comply with the NEC and local codes. Electrical inspections are performed by qualified inspectors to verify that electrical work is done safely and according to code. Inspectors check for proper wiring methods, grounding, bonding, and overcurrent protection. Understanding electrical drawings and schematics is essential for electrical work. Drawings and schematics provide detailed information about the electrical system, including the location of components, wiring connections, and circuit configurations. Electrical symbols are used to represent different electrical components on drawings and schematics. It is important to be familiar with these symbols to understand the drawings. Electrical testing and troubleshooting are important skills for maintaining and repairing electrical systems. Testing and troubleshooting involve using various instruments to measure voltage, current, resistance, and other electrical parameters. Common electrical testing instruments include multimeters, clamp meters, and insulation testers. Troubleshooting involves identifying and correcting electrical problems such as short circuits, open circuits, and ground faults. The NEC covers a wide range of topics, including general requirements, wiring methods, equipment, and special occupancies. General requirements cover basic electrical principles and safety practices. Wiring methods cover the types of wiring that can be used in different applications. Equipment covers the requirements for electrical equipment, such as panels, circuit breakers, and lighting fixtures. Special occupancies cover the requirements for electrical installations in specific types of buildings, such as hospitals and hazardous locations. The NEC is organized into chapters, articles, and sections. Chapters cover broad topics, articles cover specific subjects within a chapter, and sections provide detailed requirements. The NEC is a complex document, but it is essential for ensuring electrical safety. By following the NEC and working with qualified electricians, you can help prevent electrical shock, fire, and other hazards.